Thank you very much, Professor Yataga. It's a pleasure to be here. I'd like to thank the SPIE and all the members of the organizing committee and Professor Yataga for giving me this honor to present this talk today. It's an honor and pleasure for me to be here. This year 2015, as you know, is a very special year for all of us in the field of optics, because United Nations General Assembly designated this year as the International Year of Light and light-based technology, and also a 60th anniversary of SPIE, as you know. But there is another cause for celebration for this year. This year is 150th anniversary of the Maxwell equations. And the equations that we all love, and it's actually one of the cornerstone of a lot of work that all of us, will do in this field. And so as for preparation for this talk and another talk I was giving 4 days ago in the Meta conference in New York City, I decided to see what other equations, in addition to Maxwell's equation, play a very important role in the human endeavor and scientific and technological development. So I Googled, and I came across this book by Professor Jan Stewart, who is a mathematician and science writer. In 2012, he wrote this book, In Pursuit of the Unknown, 17 equations that changed the world. So it's very interesting, by the way. Maxwell's equation, of course, is among one of these 17, but let's just go over this quickly to see how actually our field benefited from some of these 17 equations. So what I'm going to show you in the chronological order. And according to Professor Stewart, the first of the 17 is Pythagoras' theorem in 530 BC. Logarithms by John Nepper is 1610. Calculus, the definition of derivative by Isaac Newton in 1668. Law of gravity by Isaac Newton. And wave equation by D'Alembert in 1746. Square root of -1. Now this is quite interesting that also is one of the 17 equations that according to him played very important role, changed the world, by Euler. Euler's formula for polyhedra, which relations between the number of faces of a polyhedron, the edges and the vertices that Euler found. Normal distribution by Carl Friedrich Gauss. A Fourier transform, of course, needless to say, we use that all the time. Navier-Stokes equation in 1845, and finally Maxwell's equation in 1865, 150th anniversary that we celebrate this year. Second law of thermodynamics by Boltzmann, 1874. Relativity by Einstein in 1905. Schrödinger equation, 1927. Information theory by Claude Shannon in 1949. A chaos theory by Robert May in 1975, and the 17 Black-Scholes equations related to financial derivatives and mathematical markets. And you can see, by the way, that in our field, we benefit from good number of subset of these equations that we have over here, Maxwell's equation being one of them. So it's amazing that Maxwell's equation have played such an important role in the past 150 years in development of the science and technological aspects. But before I finish the history and get to the rest of the talk, I'd like just to share with you a personal observation that I had with regard to this Maxwell's equation. A few months ago in February, I had a privilege to attend a conference called Faraday Discussions in Royal Society, and when we had been to that conference in the banquet, after the banquet, which was held in the Royal Society, there was a lot of interesting, historical items, in the glass windows around the structure, and one of the students came to me very excited and said, actually, the original paper by Maxwell is there, and in fact, you were the one who told me about it. And thanks very much, by the way, for bringing that to my attention. And so we went to that glass window, and I took my iPhone, and I took this picture, which is the original manuscript by James Clerk Maxwell. It's really, you can see the history there, right in front of you. And in fact, you can see that it looks at the number of 298 million kilometers per second, a million meter per second for speed of light. And it's interesting, by the way, that he submitted this paper in October 27, 1864 to the Philosophical Transaction of the Royal Society. And guess who was the secretary of the society receiving this manuscript? It was George Stokes, Sir George Gabriel Stokes. And it's very interesting, by the way, in fact, in the same glass window, this sentence from Maxwell's paper is highlighted, and I would like to read that. The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. And with that sentence, he changed the world. He changed the world to show that how these fields actually connected to each other, and we have benefited from his brilliant and elegant equations. And another interesting bit of history, though, when he submitted this manuscript to the Royal Society, Stokes also sent this paper for review to another scientist. Guess who that was? And you see that in the next page, but Lord Kelvin. So Lord Kelvin actually received this to referee, and that's what he has actually says over here. Let me read it from what he says. March 15, 1865. My dear Stokes, I'm sorry to have kept Maxwell's paper so long. I read it nearly through with the great interest almost immediately after it came to me, and I think it most decidedly suitable for publication in the transaction. If you can allow me to keep it a few days longer, I would be glad to have it till Monday, and unless I hear from you, I shall pass it on that day. So I guess the reviewers were also very busy in those days, just like we are now. So anyway, the paper was read in December 8, 1864, and sent to printer in June 16, 1865. And then he changed the world. So it's quite interesting that, a lot of technological development, by the way, came from Maxwell's equation. And in general, you can actually divide it into two categories. One category is the controlling the path of charge carrier, path of electrons, and that whole field of electronics. But in the case of photons, of course, we need materials to control, manipulate, and sculpt electromagnetic waves. And in fact, if you look at, a typical circuit diagram, like in this picture, all these, complicated path of wires that you see over here, essentially is there to actually map the current and show the path of electrons in order to do certain functionality. But when we come to electromagnetics and optics, then we need materials. And we need materials in order to mold the wave, in order to mold the field, in order to get certain functionalities. So if you look at the light-matter interaction, as you all know, the light-matter interaction is governed by the laws of electrodynamics, both classical as well as quantum electrodynamics. And we often would like to parameterize this relationship through a series of parameters that we all like and use, permittivity, permeability, and the list goes on. And if you look at the materials available in nature, they provide us with certain range of values, for these parameters. But then in engineering, we would like to always go beyond what nature has provided us, and the whole concept of metamaterial, or artificially engineered material, which has a long history, have come into play to actually provide artificially engineered material that will give rise to the values of those parameters beyond what nature has provided us. And indeed, if you take a look at, structure like this with the many man-made inclusions included over here, as the wave goes through here, of course, it induces electric or magnetic dipole moments, and the collective aspects of this structure would give rise to a structure, a bulk structure with effective permittivity and permeability. And the fact that you have control over the composition, alignment, arrangement, density, and host medium, and geometry and shape of this inclusion have provided engineers and scientists to come up with the materials with the unusual properties. Particularly in the past 15 years, this field has grown significantly for many reasons, one of which is the nano fabrication capabilities. And in this case, you see a variety of different examples of metamaterial. This is just a collage of some samples of materials from different groups. By no means this is exhaustive. The list can go on. And the fact that you have control over the design of these parameters has led to quite an interesting series of applications that have been discussed a lot, you know, in these SPIE conferences over the past 15 years. Cloaking, super lens and hyperlens, ultra-thin cavities, transformation optics, electrically small antennas in the microwave community, epsilon near zero and mu near zero properties, optical metatronics, and metasurfaces. And these applications have been quite exciting and really fueled the field to grow and expand. But of course, the natural question is, what do we envision, you know, in the years to come? And the fact that you have the capability to design structures to give you the parameters that you like to have for specific features and characteristics you have in mind would allow you to actually take the light-matter interaction to extreme directions. A few months ago, my good friend, Professor Nikolai Zheludev, in one of the conferences, referred to the very well-known speech by Richard Feynman in 1959, in which he mentioned there is plenty of room at the bottom. And as Nikolai mentioned quite nicely, indeed, Feynman envisioned, you know, the field of nanoscience and nanotechnology. So if we get inspiration from what Feynman said in his speech to see whether we can actually go to the extreme rather than not just the size, but to other aspects of extreme light-matter interaction, do we have plenty of room at the extreme? And these extreme could be extreme in dimensionality, could be extreme in the processing at the nanoscale, could be extreme in material parameters, and so on and so forth. So let's just talk about a few of these cases. Extreme in dimensionality. When the field of metamaterial has been evolving in the past several years, naturally, first we think about the three-dimensional structure in which this inclusion are included. But due to the limitation on the nanofabrication, or actually its practicality in nanofabrication, and also some of the very interesting scientific aspects, the field also evolved into a few directions, one of which is the area of metasurfaces. Here you can see some of the examples of the groups that have worked, you know, on the area of metasurfaces, and these are the two-dimensional version of metamaterial, kind of analogous to in the field of electronics, that the planar structures are more, you know, suitable for the nanofabrications, and the layered structure can be formed. Similar things and analogous things can be happen in the field of metamaterials. Now, one might ask that if we're going in the direction of metasurfaces, what would be the thinnest possible metasurface you can imagine? Well, one good answer to that is, of course, graphene, which is one atom thick array of carbon atoms. And as you know, field of graphene, you know, has seen fantastic development, particularly, you know, in the transport aspects of charged particles. But recently, by the way, of course, in the case of photonics and plasmonic aspects of the field of graphene. So in year 2011, one of my students, Ashkan Vakil, and myself proposed the following idea, that what if we would consider one sheet of graphene, the different patches on this sheet of graphene, which is one single atom thick structure, would have different conductivity due to the different processing like chemical doping or electrical doping. And indeed, if you do that, then the surface wave that is highly confined to the surface of the graphene, as it propagates along this boundary, is going to actually encounter these patches, and certain interesting functionality can be envisioned for that. For example, if you look at this computer simulation that we have done, you notice that you can actually have one atom thick optical devices over here. In this picture that you see over here in this computer simulation, different region of this one sheet of graphene assumed to have different conductivity. As a result, by the proper design, you can actually confine the surface wave along this one atom thick structures, and you can actually bend it and do the functionality you would like to have. With that idea in mind, you can envision what would happen in the future. If you actually look at some of the well-known, three-dimensional devices from the microwave, you can bring those concepts into the photonic area, particularly in the mid-IR, on the one single atom structure like this, as you can see. You can actually have a bend waveguide, you can have a splitter, and you can have an optical fiber, all being envisioned with one atom thick structures. 1 year after our theory paper came out, two experimental groups, both of them are good friends of ours, Professor Dmitry Basov from UC San Diego here in San Diego, and the group of Frank Coppens, Rainer Hillenbrand, and Garcia Diabajo from ICFO, Institute of Nanophotonics in Spain, experimentally verified the existence of the surface wave known as surface plasmon polariton along the single sheet of graphene. So this is quite exciting, showing that there's a possibility in the future exists that you can actually bring optical devices on one atom thick structures. Now, one of the things we are currently working on right now is to actually hybridize the system of graphene with the dielectric waveguides, coming with the situations that you can actually envision that you have one sheet of graphene wrapped around the optical fiber with a diameter much, much smaller than the typical optical fiber you can imagine. In this structure, you can have a hybrid mode, and this mode can actually confine, even though the diameter of the structure could be much less than the wavelength of operation. In this computer simulation, you can see that indeed you can confine the guided wave into a very, very small diameter structure you have. Now, moving along to another extreme scenario, and that is information processing at the extreme. Now, obviously, one of the very interesting aspects of any wave propagation is the ability to do processing, information processing. And for that, we got inspiration from electronics. Now, electronics have seen fantastic development, by the way, in the 20th century, and in the 21st century it continues to evolve. And one of the beautiful aspects of electronics is that it can actually lead to a lot of exciting processing that we all experience in everyday life, computer and so on and so forth. So, one of the reasons behind success of electronics is the fact that in electronics we have, first of all, control of motion of charged particles, and perhaps equally importantly also is the fact that in electronics you have modular system. You have circuit element, you have lumped circuit elements. So inspired by that, in year 2005, we introduced the concept of optical metatronics. And this is the concept in which the nanoparticles can be designed to behave as lumped circuit elements at optical frequency. So what you can envision in this case is that you can actually design nanoparticles that behave as capacitor, inductor, and resistor at optical frequency the same way that in electronics we have, resistor, capacitor, inductor. Now, this concept can actually open the door to bring a lot of interesting possibilities from electronics into the field of nanophotonics. Indeed, the vision that we have is the following. Can materials become circuit? And with a material designed to become circuit, can it be designed to actually do information processing? So imagine that you can actually put properly designed nanoparticles with the proper material, size, and shape, and you put them juxtaposed next to each other with the design such that when you actually send a wave to this collection of these nanoparticles, by the time that wave comes out, it will have evolved such that it will do the processing you like to have. Indeed, what this is, as I mentioned, is inspired by what we do in electronics all the time. So now, with the possibility of putting these nanoparticles next to each other, you can envision that these can also be done at in the optics at the nanoscale. So what you see in this picture is that if you have certain relationship between input and output that ordinarily we do in electronics, now can that be done also in the field of nano-optics? Just to give you an idea, by the way, what the values of these capacitance and inductance we are talking about, here I give you two numbers over here, just simple numbers that you can actually evaluate based on the formulation that we derived. That if you have a nanoparticles made of different materials, in this particular example, one of them silica and the other one silver, you see that for the silica with a 60 nanometer diameter, if you illuminate that with the helium neon laser, this particle behaves as an impedance, as an optical impedance, equivalent of an impedance of a capacitor with the capacitance of few attofarad. And this attofarad is almost 6 orders of magnitude smaller than the typical capacitor you have in electronics, in the order of picofarad, usually we do with electronics. And likewise, if you have a silver nanoparticles and you do the same for them, you get something equivalent of a few femtohenry. So these capacitances and inductances are extremely small compared with typical capacitor and inductor we have in electronics. And this indeed the good news. Because what we really have usually when you design any circuit, one of the bottleneck of the speed of the circuit is RC time constant. So if we can reduce the capacitance of the structure, that circuit inherently becomes very fast. And this naturally has very, very, very small capacitance. So this circuit inherently is a very, very fast circuit. And another thing, by the way, is that if you get these two particles, one of which behaves as a capacitor, another one behaves as an inductor at optical frequency, and you put them next to each other, what do you expect to get? You expect to get an RLC circuit. So this actually could be quite fascinating and has been actually have effect in the various fields. Like, for example, in chemistry, you can actually design these core shell nanoparticles. And these core shell nanoparticles indeed behave as your RLC circuit at optical frequency. So in 2011, 2012, in my lab, we experimentally verified this concept. So this is a picture of first a Metatronic circuit in the mid-IR that we use silicon nitride to show this. And then after that, we extended this concept into the near IR using the indium tin oxide. By having properly designed, structure to behave with the functionality of circuitry that you see over here. Indeed, this structure are your lump circuit element that we can see using the properly designed, properly structured material. Now, where do we take this idea? Just like in the circuit, by the way, one of the reasons actually the field of electronics evolved very nicely, in the middle of the 20th century, is the fact that the idea of integrated circuit was introduced by Jack Kilby and Robert Noyce. And I've been fascinated and inspired by the work of Jack Kilby. This is a picture that's one of the first integrated circuit that he built. And particularly to the student and postdoc in the audience, I highly recommend that you go and actually read his patent. It's one of the most beautiful patents that's been written to show how the mixing of this complexity and simplicity can give rise to quite a fascinating possibilities. So inspired by the work of Jack Kilby, we want to see whether we can actually take the concept of Metatronic into integrated version. So one of the things we are working on that right now is to see whether the nano structure, nano layer, by using the nanofabrication, one can actually design structure that would give rise to the highly integrated optical circuitry. So in this design that you see over here, you can see that some of the concept of filter theory can be brought into the deeply sub-wavelength structure putting next to each other, and this is the result of our simulation that we see there. Another direction to take this is to actually combine this concept with the graphene. I showed you before that the graphene, if you have different patches, would have different properties with regard to the surface wave that goes through that. But those patches, by the way, can have actually interesting circuit properties. So if you can envision, structure like this having different patch, and different patch would have different conductivities there, So essentially, you can think about that you have a collection of RLC circuits, but these RLC circuits would be one atom thick structures. So this will show us the possibility in the future to have one atom thick circuit, like inductor and capacitor in the mid-IR. And because of original motivation was about information processing, could this collection of the nanoparticle and nanostructure lead to interesting processor in the future? Just like in electronics, you put things together, as I mentioned, you have this electronic processor. Could we combine these nanoparticles in order to have some form of analog processing or analog computing? So this is the cartoon showing, you know, our vision. Imagine that you can design layered structures of a properly designed material such that when you actually send a wave at the input of this with some arbitrary profile, as the wave propagates through this very, very tiny structure, by the time it comes out, would have a different profile such that the output profile would be certain mathematical operation on the input profile. For example, could we actually have the concept of analog computer at the nanoscale using the wave propagation? So, So indeed, we considered this and we studied this concept, and we showed that that indeed it's possible to design metasurfaces that would do this. In our theory paper that came out, you know, last January 2014, we showed that it's indeed possible to actually design a layered structure that would do certain mathematical functionality. Here I'm going to show you the computer simulation of one of these functions in the interest of time. I show you only one of these, but there are other examples in the paper that you can see. In this case, with this structure design, in this simulation, you see that when you actually send an arbitrary input to the structure, as the wave propagates through this three-segment structure in metasurface being the one in the middle, the wave goes through the structure. By the time it comes out, resembles the derivative of the input. And so one thing I would like to point out that in this design, the total length of the structure in our design was about 24.3 wavelengths. Much, much, much smaller than the standard optical processor that one would use these days. So in the future, there's a possibility to actually compress the size of this processor to much smaller scale. But even with that one, we were not happy because 24.3 is still longer than what we really hope to have. And that is, we would like to see whether we can bring that to the size of about 1 wavelength. So what we did, we completely changed our approach. We said, why don't we actually try to come out with a layered structure that would actually engineer the kernel of the operator you would like to have, kind of like a Green's function engineering or kernel engineering. So in this structure, we wanted to actually design layered structure. In this case, we happen to choose 10 layers, but there's nothing magical about 10, in order to actually give us the kernel that would do the operation of the second derivative. Now, why second derivative? Because one of the interesting points in the image processing, and many of you know, the operation of Laplacian or second derivative is a very good operator for edge detection in image processing. So we wanted to see whether this layered structure can be designed as thin as possible in order to actually give us the analog way of actually doing the edge detection. So what we did in the design that we got over here in our computer simulation, we input some skyline, and we'll let actually the wave go through the structure and look at the output. And when you look at the output, indeed, you can see that the edges of the building will pop up over here in this structure. So, so this is one of the directions we would like to take this concept, to see whether it would be possible that the metamaterial can help us to have very, very thin structure that would do the analog processing for us for the process of edge detection. If this would be possible, that actually could be quite interesting, because then you don't need to actually go through the scanning of the image. This entire structure can be put on the focal plenary and just look at the output of that to see whether we can actually have the image detection. There are other applications that we are pursuing in this direction with regard to various different aspects of image processing to see whether metamaterial can play a role there. But the longer term goal we have is beyond that. So if metamaterial can be designed in order to do the information processing for us, and hopefully as thin as possible and as, compact as possible, would it be possible that one day we would have metamaterial that actually would solve equation for us? After all, if we would like to solve equation, we need to actually have a structure that will give rise to a function that would solve any arbitrary equation you would like to have. In this case, for example, I put over here two standard set of equations like differential equation and integral equation. And already we have shown that it's possible to design structure that will take the derivative, for example, or take the integral. So the next step is how to take this structure that I showed you in the design we have and try to make it such that it would solve equation for us. There's a big difference between a structure that actually would do the processing for us and the structure that would solve equation for us. So the things that's missing over here, and that's one of the things we are working on it right now, is to actually have a feedback system. If you have a feedback system in the structure, then you have a closed system whose eigensolution will be the solution to the equation you would like to solve. So one of the things we are envisioning in this thing, that if we start with the structure that I showed you and put it into a closed loop system, could wave propagation as it goes through this actually speed out the solution to the equation you would like to have. Particularly, this becomes important in problems involving the integral equations than considering the differential equation. Integral equation, as you all know, is much harder to solve because you have to discretize the system and then you have to invert the matrix. If this system would be possible, that would give rise to the solution just directly from the solution of the wave equation that you have, would be the proper kernel that you need to design. So one of the interesting points that we are working on it is this design of this kernel that we will have there. Now, moving along, another extreme direction that I would like to share with you is the extreme in parameters and extreme in cavity resonators. Now, I mentioned about the processing so far, and the processing is to actually bring the system to as small a volume as possible in order to take into account the interaction of light with the specific structure that you design. On the other hand, in many of the processing that you need to have, you have different elements, different devices you have. Certainly cavity is one of the elements that we use that all the time in optical system. Now, when we talk about cavity, they've always told us that if I have, just a standard cavity, let's assume, for example, I get the very, very simplest possible cavity you can imagine with the impenetrable walls, and you have a medium there. We know that this cavity has certain resonant frequency with certain quality factor. Now, typically, if I get this cavity and I modify the shape of this, obviously the resonant frequency will change. If we have a vision towards, a flexible photonics, if you would like to have a structure that if you bend, if you fold, you don't want the optical property of the structure change, then one thing we need to do at one of the steps is to see whether we can have cavity resonators that we actually, when you change, its resonant frequency would not change. Is it possible to have that? So at first it may look like, it's counterintuitive, because if you say a cavity has a high Q, then any small change that you make on the body of that is going to change its resonant frequency. But can field of metamaterial help us to address this, at least seemingly impossible problem? So the idea is the following. What kind of material we can design that when we put that material inside the cavity, even though the cavity would have high Q from the point of view of temporal variation, but if you actually change the shape of this cavity or deform the body of this cavity, the resonant frequency would not change. And the answer is yes, that's actually possible. And those are actually the material, which we call it material with effective permittivity and effective permeability near zero. Now, I don't have time to go through some of the detail of this that we are working on this right now, but let me just show you some of the interesting characteristics of this material. First of all, first thing comes to your mind is that, okay, do we have a material with permittivity near zero? Or do we have a material with effective permeability near zero? And even worse than that, do we have a material that both of them will be zero at the frequency of interest? The answer is yes, that's actually possible. So how do we make such epsilon and mu near zero material? There are different ways of doing that, but let me start with one way of doing that, and that is start with a material whose permittivity or effective permittivity is near zero. There are several, possibilities for such materials. Many classes of transparent conducting oxide, they have interesting properties that the real part of the permittivity crosses zero at certain wavelength, particularly in the case of transparent conducting oxide near IR. For example, indium tin oxide, the real part of permittivity crosses zero at about 1.3 micron. And if the imaginary part of the permittivity is small, that material can be categorized as the ENZ or epsilon near zero structure. Another good example of that in mid-IR is silicon carbide. Silicon carbide is about 10.3 micron. The real part of permittivity is near zero. And the imaginary part of that, provided that it's prepared properly, could be quite small. Now, my friend Nikolai Zhelodev recently studied, topological insulator, and this is a curve from his work showing that in the UV regime, around 200 nanometer, the real part of permittivity could be near zero. So indeed, some of the aspects of topological insulator in the UV could be categorized as epsilon near zero material. But you might say that, okay, that's fine, but I would like to have material at the wavelength that I'm interested, not necessarily at some of the wavelengths that nature has given us. Well, that's the whole essence of the field of metamaterial. So one way to actually make the material with the real part of permittivity near zero is by proper stacking material with the permittivity positive and negative with the proper ratio of thicknesses. You can have that. Indeed, in collaboration with Albert Pullman at the Institute of Nanophotonics in Amsterdam, he and I showed that indeed by collection of, by stacking of the silver and silicon nitride, you can actually have material with effective permittivity near zero. And last but not least, for those of you who have interest in microwave devices, actually you can imitate effectively the epsilon near zero properties if you actually use a simple parallel plate waveguide. If you actually get a parallel plate waveguide and you operate with the TE10 mode and you operate it near its cutoff, the wave propagation resembles the propagation inside the material with effective permittivity near zero. So having the epsilon near zero material is possible. The question is, how can we make both of them equal to zero with epsilon and mu? So one way of doing that is that if you actually get one of these material of epsilon near zero and put a dielectric rod inside of this structure. Back in 2007, Mario Silverino, one of my colleagues, and myself actually studied this problem. And indeed, we showed theoretically that it's possible to actually create a structure that effectively, and I emphasize the word effectively, in other words, as a bulk, effective permittivity and permeability would be near zero. Actually, the problem becomes simpler than we thought, because if this dielectric rod that you put over here have a circular cross-section, then the formula for effective permittivity becomes this simple formula that you can see over here. Now, one of the interesting outcome of this formula is the following. If you actually look at the formula, you notice that in order for effective mu to be zero, we need to make sure this expression is equal to zero. But this expression depends on the radius of this cylinder and the material, the permittivity of this cylinder, which is the regular permittivity. But it also depends on the area of this ENZ region. but it's just the area of the ENZ region, not its shape. This is actually quite interesting. In other words, it's important to have the area that you need. And I'm going to show you, by the way, in the next slide what that means actually in order to form a cavity of that. But I'd like to mention also there is another way to actually create effective permittivity and permeability near zero, and this is suggested by Professor C.T. Chen from Hong Kong University of Science and Technology. If you use photonic band gap structure and you design them to have a Dirac cone with accidental degeneracy. If you do that, the effective index of this material would be near zero, and you can have similar properties in some of the structure you need to have. So, in this case, I'm going to show you a series of field distribution inside a two-dimensional cavity that we can envision for this type of structure. So imagine that you have a cavity with a perfect conducting wall and with the epsilon near zero field with the dielectric rod you put over here. And this is the field distribution for the resonance of this cavity. But if you actually move the rod over here, ordinarily you would expect that the resonant frequency of this cavity will change. It does not. It actually stays at that point. You bring it to the corner, still stay at that point. Better yet, you can actually deform this cavity and still, the resonant frequency of that stay the same, like this. But this has the same area cross-section that you had another one, but it's a very different shape and still the same resonant frequency. You can mold it, you can actually shape the structure or this, or you can do it like this, or you can do it with this, unusual shape, or you can do it with this unusual shape, or this one. All of these will have the same resonant frequency. And there's nothing magical about this particular 7 example I showed you over here. You can actually completely deform it as long as you keep the area of that the same. This cavity will actually have the same resonant frequency. This is one of the reasons we are interested. The reason we're interested with this is because we're interested in the concept of flexible photonics. Could this be an interesting, cavity for such platform? We extended this to the three-dimensional scenario of that. In the three-dimensional scenario, I don't have time to go through the detail of this, but in three-dimensional scenario, actually, the condition is even more relaxed. Even the volume should not stay, just like the two-dimensional case of the area. So in this case, for example, in this simulation, you see that how the magnetic field is confined within that particle, but the electric field is coming out, and this cavity indeed have the same resonant frequency, all of these things there. Now, so right now we are actually in the middle of experiment. So we build this structure. First, we wanted to experiment that in the microwave regime, because in the microwave regime the size is bigger. We can understand the physics of the problem and debug the problem before we go to the nanoscale. And so here you see the picture of one of these cavity structure with a very arbitrary shape that we designed and built. And we are collecting the data right now, and hopefully very soon we're going to finish the experiment, and then we compare it with the theory that we developed over here. And so this shows that it's indeed possible that metamaterial can provide us the very unusual extreme case of cavity resonators that would have a high Q as far as the temporal resolution is concerned, but from the spatial point of view, it's flexible without changing its resonant frequency. There's another reason we are interested in and that is to bring this concept into quantum optics. What kind of quantum electrodynamical features such structures have? For example, can it lead to superradiance? Can it lead to subradiance? How about long-range collective state of multi-emitters in these structures? How about the long-range entanglement that happens over here? And last but not least, how this would actually affect the cavity quantum electrodynamics. This type of structure would be very unusual light-matter interaction, and so we are studying some of these concepts to see how the extreme case of metamaterial would actually have effect on the cavity quantum electrodynamics. So with that brings me to my summary, showing that in fact materials, particularly the concept of metamaterial, can provide us to sculpt the wave. To sculpt the wave in order to give you the functionality and unusual features that you're interested to have. I showed you some of these concepts that we have. For example, the extreme scenarios, the extreme in dimensionality, the extreme in the processing in the nanoscale, the extreme in dealing with material parameters can lead to unusual features. And the processing, by the way, could be another interesting direction to take these structures. Flexible photonics would be another area on that, and particularly also the quantum optical aspects and some of the features that this may lead to, particularly with regard to the entanglement and related issue. So I thank you very much for your attention. Thank you.